anyone has your homework, so I can take them up here. Okay, were there any particular difficulties with this homework assignment? Okay, well, I guess we can get started with today's material. So this is the last lecture of the class. So when we get back from the Thanksgiving break, you guys will be doing the lecturing. So what I wanted to do is kind of wrap up with an important issue that cuts across many of our problems in studies of model analysis, and that's the question of model validation. The basic issue we're dealing with here is that we built a model. It might be an optimization model, it might be a sampling model. We've taken some data, we've trained the model for the data, and then what we want to ask in some sense is our model good? So we've got, let's say, the best model we can put together given the class of models we're looking at and given the data and given the algorithms available to us, but is it in any objective sense a good model? And that's basically the question I wanted to look at today and to kind of use as something we can use to wrap up this class. Right, so often this question of model goodness is something we're building into how we learn the model in the first place. So whether we're doing a model as an optimization problem or a sampling problem, we're usually trying to learn some features of the models. We're usually learning a model structure or model parameters using various techniques we've learned in the past few weeks. And often we're trying to do that to optimize some measure of goodness. So we've seen, for example, that often we'll pose our models in terms of a least squares measure or mean square deviation, something like that, where maybe we've got some set of data available to us. So we've got real data. Maybe that consists of some data points, T1, Y1, T2, Y2, and so forth. And we've got our model predictions. So we can run the model and see what the model would do at the same data points and get a model T1, Y1 hat, T2, Y2 hat, and so forth. And we can ask in the design of this model what parameters are going to give us a model that maybe minimizes the sum of the squares of these differences between the observed and estimated values of y, so the sum of y minus y hat squared. And that might be something that we've tuned the model to solve. So in that sense, we're starting with some idea of what a good model looks like, and we've built it into the problem that we're getting the best model we possibly can given our data. So does this sound familiar to everyone? All right, so there are more sophisticated ways of doing this. So least squares models tend to be good under certain assumptions about parameters of the models. They tend to be good under certain kinds of noise assumptions, and they tend to be something for many kinds of models that we can infer efficiently. But often we would want to use something like a more sophisticated maximum likelihood model. There are some special cases in which a least squares model is a maximum likelihood model for a particular likelihood. But in the more general case, we might have some maximization we're trying to do over maybe a model structure, G, and a set of model parameters, lambda. And we're trying to maximize some probability of an observed data set, let's say X, given lambda and G. And maybe we also have some prior estimates of how intrinsically good different models might be. So we might have a prior on G that maybe tells us that some particular models are well supported for our data. So if we're looking at network models, for example, it might be that the prior is encoding that some network edges are well supported by the literature, or it might just be a model that's encoding a prior belief that simpler models are better, so penalizing for complexity of G. And you can likewise have priors on the parameters. So we might have continuous parameters like constants relating to the rates on edges of this network model. And we likewise might have some prior estimates of what these should look like. Maybe we believe we know for some transcription factors how strongly they bind to the DNA A, or we can estimate that from structural models or from literature, and we could build that into our model. But in some sense, what we're encoding is some belief about the universe of possible models and how intrinsically good any model is from that universe, given our prior knowledge and given whatever data we have available. So in some sense, just in learning models, we are trying to figure out if we have a good model. And we can use these same measures, these same objective functions for which we're learning the model as a measure of model goodness. But there are problems with that. So can anyone think of why we might not want to do this? Why would it be wrong to, let's say, look at a network model, train it on a given data set, and then use the maximum likelihood we learn to assert that this is a good model?
Data may be incomplete.
Yeah, we could have incomplete data. It might be that there are other kinds of data that would be important that we want this to work on. It might be that we've simply overfit to the data we have available, so you might get a very good maximum likelihood, even though your model is actually not a good description of the full space of possible data that might really exist for that system. So there are lots of reasons why this isn't really quite the right thing to do, and we want some sort of external measure beyond the objective function we're actually using to learn the model. So we don't necessarily want to measure goodness of the model by the same notion as we use to fit the model, even though the fit of the model is in some sense trying to optimize for model goodness. And so we need to go to other kinds of measures of model goodness, other ways we can independently validate that a model we have is a good explanation of whatever system we're trying to explain. So there are a lot of ways of doing this. So some kinds of measures come from basically the study of statistics, so ways of trying to pose a statistic or some measurable property of the model with respect to the data we can use to assess whether we've got a good model or a significantly good model. So, for example, if we're training a regression model, maybe we're trying to learn a prediction of these sets of data points. Maybe we've got these different values of y as a function of t, and we train some model to those values. We'd like to know if there's a good fit to those values. It might be that we can look at this in terms of, let's say, a correlation coefficient. So we can go after the fact and we can say, we've got our measured values y, we've got our predicted values y hat, and we can see how plotting for individual points on this plane of y and y hat falls within the plane. And in principle, if we have good predictions, then we should see that most points more or less lie along a diagonal of y equals y hat. And you can quantify that with measures like the correlation coefficient, which we had seen in the previous class, is the covariant of y and y hat, divided by the square root of the variances. And that kind of measure can be useful in some situations. It can give us ways of assessing whether the similarity between the model and the data is more than could be explained by chance. Essentially, the whole field of statistics is really devoted to that question of deciding whether models are good, in the sense of deciding whether it's possible the model could have fit the data by chance, and trying to specifically reject that hypothesis. There are other ways of doing this we could think about. So we had seen last time some measures from the field of information theory. That gives us another way of thinking about goodness of a model. So information theory is the study of entropy, or effectively a way of quantifying the number of bits of information carried by any particular signal. And one way of thinking about the goodness of a model is that the model is something that lowers the amount of information in the data with respect to the model. So if we think about one of the models that we had studied when we looked at expectation maximization, one of these haplotype models, where we had some genotype data So ambiguous 0, 1, 2 data, where 2 means you've got a 0 and a 1 means you've got 2 1s, 0 means you've got 2 zeros. Then in that example, we had seen that you can take a set of data and you could propose a model of that data. So we can say that there is a model that there is some maybe pair of haplotypes actually out there, 1, 1, 1, 0, 0, and 0, 0, 1, 0, let's say. Maybe this has frequency 90%, and this has frequency 10%. And then we can talk about what the probability of generating any particular set of data, any particular set of genotype data is for that universe of possible haplotypes, for that model, the haplotype structure. You can use that to create a likelihood model, so we can talk about, in terms of this model, what is the likelihood of your genotype data, but we could also use this to create an entropy model by talking about the sum of the probability of our data, that is the set of genotypes, given our model, times log probability, data given model, and get what's called the conditional entropy of the data with respect to the model. And I'll assert that this gives us a way of thinking about whether we have a good model for a particular data set. Can anyone explain why that would be the case? Why would it make sense that if this number is small, you have a good model? Well, effectively, what low entropy is saying is that most of the complexity in the data is actually contained in the model. If you've got a good model, then it's providing a good explanation for why the data takes the particular form it has, or why you have this particular distribution of data. If you've got a bad model, then you need a lot of extra information beyond the model to explain why you have this particular set of data. So that's why these kinds of information theoretic measures can often give you a different way of thinking about these problems that can be independent of maybe how you learn the model, give you a way of thinking about them that can evaluate whether you've got a particularly good model. You can often represent entropy models as a kind of likelihood model. So that to some degree they're equivalent, but it's another way of working with these kinds of systems. Even if we've got good measures like this, and there are a lot more of these that I don't have time to go into here, you have to be careful about what you're measuring. So let's say we are looking at a model of Brownian motion. That's something we talked about how to simulate. So if we study a Brownian motion process, and we see some particle moving around, and we develop a class of model for simulating this, maybe a stochastic differential equation, and we learn some parameters of that model, and we observe that maybe the stochastic differential equation does this. Is that a good model? It's not necessarily easy to ask that question because the model may be doing something very different than the real data. We can't just ask, do the trajectories overlap, because we're looking at a stochastic system. So we have to come up with some other way of thinking about how we would measure the goodness of our model with respect to our data. So can anyone think of how we might do that? What might be a measure of whether we have a good model? In a case like this, you'd often try to come up with some kind of statistics or some kind of quantity you can use that will give you a measure of the real data that would discriminate between different possible models that might be generating it. And then we can ask, does our model behave according to the same statistic? So maybe if we're simulating Brownian motion, we might say that our statistic is the well, it could be that we're going to propose that our models look like something like the distance from the origin, so the mean value of maybe our model squared or our real data squared, we think is described by something like square root of the amount of time that's elapsed, or square of the amount of time, or the amount of time times a constant or whatever. And maybe we would try to say, what is the best fit coefficient A and the best fit exponent B? And then we can say, for the model we've learned, does it match the exponent and the coefficient? For an SDE, the coefficient might be identically 1, and we can ask if that's fit by our real data. And it might be that the A is something we've learned, and we can ask how accurately the A we measure from the real data fits the A we get from simulating our model. So these are all just ways that we might need to think about this, and I'm just saying this to make the point that you often need to be kind of careful about what you're measuring. It's not necessarily obvious how we would think about the problem of finding a good fit for a particular model, or finding a good way of evaluating whether the model is in fact a good fit to the data. Even that still has problems, though, because it can be tricky to figure out if what you're trying to use as your measure of goodness of fit is really independent of the way you use to fit the model. So, for example, if we learn a maximum likelihood model and then we measure whether it's good based on its the conditional entropy of the data given the model, those aren't really independent ways of assessing goodness of fit. They may be subtly different models. Depending on how we pose the likelihood, you might actually be doing exactly the same thing. You might end up with an entropy measure that is exactly the same or equivalent to your likelihood measure, the log likelihood. And so you still need to be a little careful there to come up with some way of assessing whether your model is good. And very often the best way to do this is to try to figure out why you're creating your model and to try to come up with some real assessment of how good your model is for whatever task it's meant to solve. So an example of this would be that very often we're creating a model to perform some kind of prediction test. So let's say that we are trying to come up with something that will test whether a person has a particular disease. So maybe we are looking at a problem that's similar to one in the homework you guys should have been working on for the past week and a half, where you've got a set of biomarkers and you're trying to figure out from these biomarkers, does a person likely have a hidden tumor? So a tumor you can't see yet that maybe would justify performing an MRI or whatever to see if they really have it. Well, we might propose to solve that by taking these biomarker measurements, maybe measuring amounts of different proteins in the bloodstream, and training a regression model where we train some kind of score X based on quantities of, or score Y based on quantities of biomarkers X1, X2, X3, and so forth. So we learn some coefficients, A, B, C, and D, where we'll assert that Y is going to be something that tells us some measure of how confident we are that the person has the disease. And maybe we put in a threshold, so we say if Y is greater than 0, we'll predict the person has the disease. If Y is less than 0, we predict the person does not have the disease, that person is healthy. In this case, we may be literally learning a regression model, but we have a real-world application we're trying to develop this for, and so we can try to assess the goodness of the model based on the application we're trying to solve here, so based on the classification test. And that in itself introduces all kinds of subtleties we need to be careful of in studying this kind of model. So to see why that's the case, let's imagine that we've done this, and maybe we've tried it a few different ways. So maybe we've tried different prior probabilities or different places of putting our threshold to decide who's got the disease and who doesn't. And we've ended up with two different models. So let's suppose we've got model 1. And we'll imagine that we're looking at a disease that maybe 1% of the population has. So it's not a very common disease, but it's common enough. And then we can look at the predictions this model makes on a population. There are going to be some people who have the disease, and I've asserted that it's 1% of the population, and some fraction of those the model will say has the disease. These are known as the true positives. And it might be that we've got a model that always gets it right when the person has the disease. So in this situation, that would mean our rate of true positives is 1%. We might also have some people who don't have the disease, but the model says they have the disease. Those you know of as false positives. And maybe we're going to assert that in this model, the false positive rate is also 1%. So 99% of the people don't have the disease, but 1% out of that 99 it asserts do have the disease. We might also have true negatives, which are people who don't have the disease. Those who have 98%, so don't have the disease, and the model says they don't have the disease. And we could have false negatives. And I've already asserted that the model always gets it right when it says when someone actually has the disease. So the false negative rate, so the rate of people who have the disease but it says don't, would be 0%. And then this model, we would say, has an overall accuracy, which is the sum of the true positives and the true negatives. So we would say that the accuracy then is 99%. And we might say that this is a pretty good model, but we also might say that this is not such a good model. So if, for example, we are really interested in not getting it wrong when the model says someone has the disease, we might think that even though this is a 99% accurate model, it's actually a pretty bad model because half the time when it says someone has the disease, they actually don't. Maybe we create this model again, tuning it to try to be less likely to give these false positives, and we come up with another model that never gets a false positive. It never says someone has the disease if they don't, but it accomplishes it as follows. It gets 99% true negatives, gets 1% false negatives, and then 0% true positives. So in plain English, can anyone tell me what this model does? This is
a model that says you don't have the disease.
Yeah, so this is a model that always says you don't have the disease. No matter what the biomarkers say, it says you don't have the disease. And that model is, by the accuracy measure, just as good as this model. And superficially, we might think that this model is useless. It carries no information because it always makes the same prediction, whereas this one is doing, we might think, a decent job. And yet the accuracy measure is identical for these two models. So that kind of reveals that accuracy is not necessarily a good way to think about this, or at least by itself is not an adequate way to think about whether we have a good model. Now there can actually be some cases where model 2 is the better model for this kind of system. Can anyone think of how that might be the case? What could be a situation where we actually prefer model 2? Well, it might be that maybe the disease we're testing for is not actually a very big deal for the patient, but maybe it's something that's very stigmatized in our society, so it's actually really bad to tell someone they have the disease when they don't, and it really doesn't matter if you tell them they don't have the disease when they do. So that might be a case where this is actually a better model for our applications. You really have to pay attention to what your application is. There are many other kinds of situations where something like this comes up. So if we're looking at, let's say, a model for predicting transcription factor binding motifs in DNA, it might be that in some cases we want to be very conservative in our predictions. So we don't want to predict lots of transcription factors that aren't there because maybe we're building a regulatory model or trying to build a network model, and we need a very conservative pre-screening to make our network inference computationally tractable. But in other cases, maybe we want to be sure we haven't missed anything. So So we want to be really sure we have no false negatives, and we'll tolerate a large number of false positives. We want to get all the real transcription factor binding sites, even if we get some fake ones, because we'll just learn that the fake ones are not actually predictive later in our analysis. So because of all of this, we often need to be a bit more nuanced in how we think about the accuracy of a model. And there are a number of different measures that have been developed to kind of capture these different aspects of accuracy we might care about. So one version of this you'll often see is the sensitivity of the model. So the sensitivity of a model is defined in terms of these different quantities here, true positive, false positive, and so forth, as the number of true positives divided by true positives plus false negatives. So what this is telling us basically is, of the things the model finds, of the things the model should be finding, I guess I should say, of the things the model should find, what fraction of them does it actually find? So if we're trying to make that motif finder that never misses the real motifs, even if it gets extra ones, that would be a case where sensitivity is the thing that's very important to us. We want a very sensitive predictor, even if it's getting lots of mistakes in terms of over-prediction. This is also sometimes known as recall, so you'll see those terms used interchangeably. There are a couple of other things that capture the alternative here, that we don't want a model that over-predicts. One of them is the precision of the model. And precision is defined as the number of true positives divided by true positives plus false positives. So can anyone say in plain English what this means? What is this capturing about a model, the precision? It's telling us of the things the model says are what we're looking for, what fraction of those are actually what we're looking for. So it's related to the sensitivity, but it's a subtly different question. So the sensitivity is asking, of the things we should find, what fraction of them do we find? This is asking, of the things we find, what fraction of them should we have found? So it may be that if we are looking at a motif finder, we're willing to tolerate low precision. We're willing to tolerate lots of false positives, but we really want high sensitivity. Whereas in the disease case, maybe it's really bad to have false positives. We want very high precision, and we'll tolerate lower sensitivity to get that. Does that make sense to everyone? You'll sometimes see, to capture sort of the same idea, what's called the specificity. So the specificity is the true negatives over true negatives plus false positives. Basically, it's capturing how often does it say something shouldn't be there when it actually shouldn't be there. What fraction of the things it says shouldn't be there actually shouldn't be there. And you can reason more or less in the same way about the trade-off between sensitivity and precision versus sensitivity and specificity, even though the precision and specificity are two different kinds of quantities. Basically, you can almost pick any two of these and they'll capture what you're trying to get at. But usually you'll see this presented as either a trade-off between sensitivity and specificity or precision and recall. So any questions about any of that? All right, so very often in a model like this, we'll have some ability to trade off between these different factors. So it might be that we are inferring one of these motif finders, and we'll have a prior probability we can plug in. So prior expectation of how common those motifs are. And if you turn that prior probability very high, we might end up with a model that has very high sensitivity but low precision. And if you turn that prior probability low, you end up with a model that has low sensitivity and high precision. So that kind of trade-off comes up very often in these sorts of modeling contexts. And to help understand that, there's a common kind of visualization called a receiver operating characteristic or ROC curve. And a ROC curve looks something like the following. We plot the sensitivity or recall on one axis, and we plot 1 minus the precision on the other axis. This 1 minus the precision is something also known as the false discovery rate, or FDR. So we can think of that as being equivalent to the false positives divided by false positives plus true positive. And FDR is basically just equivalent to thinking about precision, just 1 minus that. And typically what a receiver operating characteristic curve is going to look like is something like the following. There might be one range of parameters where you end up with very low 1 minus precision, so high precision, but poor recall. And as we tune the parameter, you'll tend to trade off between them. So you turn up the parameter that's increasing your recall, and you start losing precision, so you get a curve that looks something like this. It might be that under different conditions or different kinds of models, you can get different sorts of trade-offs. So maybe we train one kind of model and we tune the priors, and for different values of the prior parameter, we get various data points along this curve, and we can try a different class of models, and maybe it will trade off between these parameters in different ways. So maybe a different model gives a curve that looks something like this. So can anyone tell me how might we decide which of these two models to use? Let's say this is model 1 and this is model 2. Which is a better model, model 1 or model 2? Well, there's no right answer, really. It depends on what you're trying to do with them. So if we're working in one of the applications where we need very high sensitivity, then what we might say is we'll start by deciding we want high sensitivity. We'll see which model gives us better sensitivity, and we could end up saying, well, it looks like model 2 is better in that kind of domain, whereas if we need high precision, maybe we want to stick with model 1 and tune it to this end of the domain. A way that's often done in practice is to use the false discovery rate. And often what we will want to do is to say that we'll fix a false discovery rate we're willing to tolerate, and then we'll ask for that false discovery rate, what's the best we can do with our model. So maybe we decide that our false discovery rate is here. This is the false discovery rate we want. And we can then say, okay, given that false discovery rate, there's an optimal parameter tuning for model 1 that will give us this recall, an optimal tuning for model 2 that will give us this recall, and then we can say model 2 is the better one at that given false discovery rate. That's often how people would handle this kind of question in practice. So are there any questions about any of this so far? Okay, so that is basically giving some of the many ways that we quantify how good a model is, or whether a model is suitable for a particular purpose, but we still haven't quite solved the problem of how we really want to assess goodness of a model in practice. And a big part of the problem is that we still have this issue that we might be overfitting to a particular data set. So if we have some universe of data we're using to learn our models, then even if we go back to that same set of data and get a ROC curve, or get sensitivities or specificities or accuracies, we still have the problem that we can't really trust those because we learned the model from those data. So very often, pretty much always, when you work with a model like this, you have to do some extra things to try to assess goodness in a way that controls for the possibility of overfitting. So does anyone remember what overfitting is? So overfitting is something we had encountered when we looked at interpolation and extrapolation. So that would basically be the problem of that. If we've got lots of noisy data, if you try to learn too complicated a model, you often end up fitting the noise rather than the actual trend in the data. So a high degree regression model, for example, to this data set might look something like this, where really all it's fitting is the noise, whereas a low degree model might actually do a better job of fitting it because it's fitting the actual trend and smoothing out the noise. So that's a problem we very often need to worry about in these kinds of systems. We need to come up with some way of preventing model overfitting. Now, we had seen previously a few ways of thinking about this for various kinds of models where we could build it into our model design to try to avoid overfitting. Does anyone remember any examples of that? Let's say we're learning a genetic regulatory network model. How can you build it into the model to try to avoid overfitting, so fitting an overly complicated network for the data?
Have a like a prior data set to the number of edges and like that?
Yeah, so we can add a prior, so an anti-complexity prior. So we saw that there are some kinds of standard anti-complexity priors. So there was the Akike information criterion, or AIC, the Bayesian information criterion, or BIC, and then variations on these, so the AICC and regularized versions of these sorts of things. We can also come up with kinds of generic custom anti-complexity priors, so basically anything we can come up with that tries to force the model to be simpler or to bias it towards simpler models unless the complexity gives a significant boost in the ability of the model to fit the data. And there are some other variations on this we haven't seen yet. Well, the homework due today, you guys should have seen one version of this, so another way of doing what's called model regularization, where you can build into your objective function in a more ad hoc way some measure of how complicated the model is, and then trade that off against quality of fitting to the data. And there are other general paradigms for this kind of automatically preventing overfitting. So there's something, for example, called a minimum description length, or MDL model. So an MDL model is something that uses some of the ideas from information theory to try to do this automatically. Basically, it's a way of saying, if you take your data, and just as we had seen the conditional entropy of data with respect to a model as a measure of goodness of fit, essentially what you do is try to find a model that optimizes for conditional entropy of the data with respect to the model, plus the entropy of the model itself, so how much information we need to describe the model. And then by optimizing for those, you get kind of a balance that if you have a lot of data supporting a complicated model, you learn a more complicated model. But if your data is kind of ambiguous, then it's biased to keep your model simple, so the cost of the model description is small. So that's another example of how you can build that into the model design. But even if you use these kinds of things, you still have a risk of overfitting. So these can maybe do a better job of preventing that, but we still want to verify after the fact that we have in fact avoided overfitting in our model. So any questions about this? All right, so even if we've done a good job of setting up a nice anti-complexity prior, what we're going to want to do is go in after the fact and verify that the model is actually doing a good job of fitting the data and that it's learning the trends in the data and not just the random noise in each data point. And typically the way we're going to have to do that is to verify that if you train the model on one set of data, it's predictive of another set of data. And that basically is the topic of cross-validation. And cross-validation is a really important thing in model design. And basically, it's one of the key things, is basically a set of strategies for doing that basic task I just mentioned, trying to train a model on one set of data and then test whether it's good on a different set of data. And there are a variety of different ways of doing this. Some of these fall under the general category known as jackknifing. And jackknifing is basically a kind of deterministic way of doing this. So there are a few different versions of deterministically doing this. And the simple is what's called twofold cross-validation. So in twofold cross-validation, we look at the model we're trying to learn. We set up a universe of possible models with maybe some parameters we need to learn. And then we take the data we have available for learning this. So we've got some set of data, and then we split it into two sets. They don't necessarily need to be the same size. We have our training data, and we have our testing data. And then what we do is train the model on just the training data, so you learn all your parameters, and then we go and evaluate on the testing data. So we take our model, we learn our parameters lambda of the model, and then we plug in the testing data for the parameters we learned from the training data, and then whatever measure of goodness of fit we're using, whether it's accuracy or root mean square deviation or maximum likelihood, we say whether or not the model is good based on how well it does on the training data, independent of how well it does on the testing data. So does that make sense to everyone? You can generalize this to what's called a k-fold cross-validation. And the k-fold cross-validation, the assumption would be that we take our data and we split it into k subsets, 1, 2, 3, up through k. In this case, usually we'd be assuming that these sets are of equal size. And then the way we do this is that we take, let's say, all of the data except set 1, train on sets 2 through k, and then evaluate how well the model we get predicts the effects on set 1. Then we use all the data except set 2, train on everything but set 2, and evaluate the quality of the fit on set 2, and then just repeat that for each of the k subsets. And then we would use the accumulated accuracy or whatever measure of fit we're using across each of those k tests as our measure of how good our model is. Does that make sense to everyone? And so in the limit of this, we end up with what's called leave one out cross-validation. And leave one out cross-validation for a data set of size n is basically the same thing as n-fold cross-validation. So we take the first data point, whatever that is, remove that from the set, train on the remaining n-1 data points, then see how well the model we learned can predict that one data point. Then we repeat that for data point 2, data point 3, and so forth. So each test, you're learning a model from n-1 points and evaluating it on the remaining 1 point. And then you use that to decide whether this class of models you were learning is a good predictor for your data. And so we have all of these alternatives available. And sometimes we're going to want to do twofold, sometimes we'll want to do leave one out, sometimes k-fold. Can anyone think of how we would decide which one is appropriate? What might be a condition where we want to use leave one out cross-validation? Well, what are the trade-offs? What's a factor that would be in favor of leave one out versus twofold, let's say, at the other extreme? Well, in general, what we're trading off here is very often the computation time versus the quality of the models we're learning. So in a leave one out cross-validation, we're basically using as much data as possible to learn our model, but we're also learning the model repeatedly. So if we've got n data points, we have to learn the model n different times, but we're using almost all of our data each time we learn it. Whereas in twofold, you're only training the model once, but you're using something on the order of half of your data. So when would this versus this be a good thing to do? Let's say we've got a lot of data, so we've got a very large number of data points. Which is better, leave one out or twofold cross-validation? Yeah, twofold would generally be better if we've got a lot of data, because we don't want to have to train our model many times. So twofold, you just train once, and if you've got a lot of data, so you don't really need all of it, then twofold should give you about the same measure of accuracy as leave one out. If you've got just a few data points, then very often that's when you want to use leave one out, because every data point matters, so you want to use as many as possible in training your data set, because if you leave out half your data and you've only got a few data points, you'll learn a much worse model than you potentially could with that technique. The other thing we would often care about is how hard it is to train our model. So if we're training, let's say, a linear regression model, maybe that's something that's very easy to learn, whereas if we're training a complicated Bayesian network model, that might be something hard to learn, where we need a lot of compute time, and that might be a case where we would favor twofold cross-validation, just so we're not running a learning problem many times. So any questions about any of that? We also saw one other technique in a slightly different context that can be used for the same kind of cross-validation, and that's known as bootstrapping. Does anyone remember what bootstrapping is? So bootstrapping, it's similar to these sorts of strategies. So with bootstrapping, remember, what we would do is we would take our data set and we would construct an artificial data set by sampling from our original data set. So if we had n data points here, we would sample with replacement n data points here, and sampling with replacement means that it might be at a particular data point here, in left in our original data, could end up being copied multiple times in our new data set, and other data points here might not end up in our new data set. So effectively what we're getting is kind of a subsample of our original data set. And with bootstrapping, it's sort of like k-fold in the sense that you're picking subsets of your original data, training your model on those. You can potentially test on the ones you've left out of that. But basically what you would do is learn your model multiple times, and then you can start asking about what are the things you learn robustly, the things you learn repeatedly. We had looked at that as a way of considering uncertainty in the model, but you can also use it as a way of cross-validating your model, seeing if you get the same predictions on different subsets of the data reliably. Right, any questions about any of that? Right, so cross-validation, I'm not spending a lot of time on this, but I do want to emphasize that it is something really important in model analysis. And it's much more subtle and harder to get right than you might think. So let's say, for example, that you are developing a model and you decide to do twofold cross-validation. So we've got your data, we split it into training and testing, and maybe we're trying to learn a motif finding model, and we propose some kind of, I don't know, hidden Markov model for figuring out for identifying a particular motif. So we propose some structure to our model, and then we train that model, so we learn the parameters for that model structure, and we test it, and then we decide that the results don't look very good. So somehow having trouble learning our model. So we then go back and say, okay, maybe we needed an extra edge in our model here. So we put in that edge, we train it again, we run it on the testing data, and now the results look really good. So we then take that model, we say this is our model, we take the results of how it did on the testing data and say this is how good it is, and we declare that we found a good model. So I'm going to assert that that is not a good thing to do. What's wrong with what I just described?
We have overfitted.
Yeah, we might have overfit it. Essentially, once we looked at the results of the testing data and then went back and changed the model, we were kind of manually doing a sort of meta model learning where we no longer had a well-preserved testing data set. The testing data effectively became part of our training data once we changed our procedure based on what the model did on the testing data. And so we no longer are doing proper cross-validation. You can no longer trust the results of that model. So this is a subtle thing to get right. You have to be really careful. And in practice, most people in the field, I think, are not really careful about this kind of thing. What I just described is something that happens pretty commonly when people are developing models for various tasks in real-world scientific research, and something you have to be careful of. So in your own work, you have to be careful not to do what I just described. And it's actually really often when you get into working with scientific literature and reading about other people's methods, very often you're trying to think about whether you believe someone's results. This kind of mistake is one of the most common things you look for. One of the first things I would look for if someone presents a method and the results just seem too good to be true. So very often, even if they describe the cross-validation, they say we've got training and testing data, they might have done something like this and just not said they were doing it or just not reported it in the paper. So you need to be really careful. It's a very common way to get a result that's not really a reliable result. So any questions about any of that? Okay, so all of that is basically coming back to the question of that we have to have measures of goodness of fit. We have to cross-validate so that we know we can actually believe those measures and we're not just overfitting to the data. But often in model validation, we need to go even further than that. And very often, we care about not just whether we've learned a good model for our data, but also how robustly have we learned that model. So are there other equally good models we could have learned? Is there a high uncertainty in the model? If we had more data, could we have pinned the model down more precisely? And all of that falls under the general category of what's called sensitivity analysis. And this is another thing that I can only mention very briefly in this final lecture here, but that you really need to pay attention to when you do serious work in model inference. So basically what this comes down to is, in some way or other, assessing the uncertainty in our model inferences. So it might be, for example, that we are trying to learn a model of a biochemical system. So you've seen lots of models like that where we have A plus B goes to C, and maybe we have some data showing how A and B decay and C increases and so forth. And we're trying to learn maybe rate constants of a model like this. So maybe there are a few rate constants like K1 and K2 and maybe some other ones. And we're trying to fit our representation of this model to our data set and learn K1 and K2. It might be that we can learn a very good model, maybe even a model that is predictive on other data sets, that actually doesn't give us very accurate K1 and K2. So it might be, for example, that we run our model inference, we learn K1 and K2, but it happens that if we plugged in K1 and 2 times K2, we'd get almost exactly the same results back. That would mean that we have a model that is not sensitive to K2, and in a case like that, we might say that we don't want to report that K2 is the right value, even if it's the thing that maximizes our model fit, if a fairly large perturbation in K2 would actually give almost as good a model fit. This also is kind of a subtle concept, because there are some cases in which we want our model to be very sensitive, and there are some cases in which we want our model to be very insensitive. And as with many of the other things I'm talking about today, it really depends on what your point is in creating the model. So if our model has as its purpose finding K1 and K2, so our goal is to find K1 and K2 very accurately, do we want a sensitive model or an insensitive model? Well, if our goal is to learn the parameters, in general, what we want is a sensitive model. So we want a model where if you change the parameters a little bit, the output will change significantly, because then we know we've got the parameters very precisely. If you change them a little, you wouldn't get the same result. So you can be confident that the values you learned as the best fit to the data are actually really close to the right values, assuming other aspects of your modeling were correct. On the other hand, if our goal is to learn a model that can reproduce these curves here, then we might want an insensitive model, because maybe the data is noisy, maybe there's some uncertainty in our procedures, maybe we can't necessarily learn the optimal parameters reliably. In a case like that, we might want an insensitive model, because we'd like to know that if we made a little mistake in getting K1 or K2, and we're off by a little bit, that we're actually going to get almost the same output out of our simulator. So as with so many of these other things, you really have to pay attention to what your point is in trying to do this. There isn't necessarily one right answer here. So any questions about that? So there are some cases where we can do this sort of sensitivity analysis just directly from an analytical analysis of our model. So let's say, for the sake of argument, that we are trying to learn a rate constant for a model that says dA dt is minus Ka. So this is a model we could analyze analytically. Does anyone know what the analytical solution to that model is? What is A of t? It's going to have some initial condition, A of 0, that we would have to fit.
Exponent of minus k is
We'd have e to the A0 and e to the minus kt. So whatever k we learned, we would end up with the initial condition times e to the minus kt, and then we can verify for t equals 0, you get the initial condition, and then you get an exponential decay. So a model like this, we could analytically try perturbing it. So we could say, what happens if instead of k, we have k plus delta k? We would know that our model would be A0 e to the minus k plus delta k times t. And in a case like that, we could say that that's equivalent to e to the minus delta kt times the original model, E0, A of 0 e to the minus kt. And we could analytically analyze for a given t and k how much of a perturbation that would make to the model. So we could say that the fractional error after some time capital T for some values k and delta k would be the perturbed model, e to the minus delta kt times A of 0 e to the minus kt minus the original model, A0 e to the minus kt divided by the original model. That would give us a fractional error. And if you cancel out all of these terms of A0 e to the minus kt, we would end up with, I should put an absolute value on this, we would end up with e to the minus delta k t minus 1. And then if we assume that we had, let's say, a large t, then this could be a fairly large quantity. If we have a small t and small delta k, it would probably be a small quantity. But in general, we can infer this could be a pretty appreciable error in our model. So any questions about that? Usually, we are not going to assume that you can analytically do a sensitivity analysis on your model, but you have various alternatives there. So let's say we've trained a model like this, and we don't have an analytical expression for what the model does, but we have a universe of models and a set of parameters we've learned for our data. How might we do a sensitivity analysis to figure out how the quality of fit depends if we perturb K1 and K2? Well, if you've got a simulator, you can just try simulating it. Very often, that's what you would actually do. So we learn a model, we can plug in any K1 and K2 an amount of time and simulate these curves, and then we could try doing various perturbations. So we can try throwing random noise on top of K1 and K2, get lots of perturbed simulations, and then try to evaluate or plot in some sense the quality of fit of the model, of what region of the parameter space gives pretty good fits, what region gives not so good fits. So in general, what you would find is if you've got a very sensitive model, you would learn a space where we might have one very small basin of very high quality of fit, and then as you get further away from there, you have very poor fit. In a less sensitive model, it might be that there could be a relatively large region of parameters that all have about equally good fit, and then we can't really distinguish among the quality of the parameters within that sort of region. So that sort of more systematic analysis can be useful because often the sensitivity is not such a simple question. If you have a large number of parameters, you could have very complicated dependencies among the parameters. So it might be that K1, K2 gives a good fit, and 2K1, 2K2 gives a good fit, but K1, 2K2 doesn't, and 2K1, K2 doesn't. It might be that there's some kind of parameter dependence like that, where maybe the good fitting region of the parameter space, I don't know, it's something like that, that can be hard to figure out without an exhaustive kind of sampling. All right, so any questions about that? And another approach that we can use to solve that kind of problem, we saw just a few minutes ago, and that is the bootstrapping approach. So could anyone tell me how bootstrapping would be useful for this problem? What might we do to use bootstrapping for sensitivity analysis? Well, if we have some way of subsampling the data on which we're training our model, then very often something you would try to do is take subsamples of your training data, learn the model, take another subsample, learn the model, and just do this repeatedly. And then we could come up with some notion of the set of parameters we learn on these repeated trials. So if we've got the two parameters in isolation, say K1 and K2, it might be that when we do lots of bootstrap trials, maybe we infer that there is a particular mean value. We learn that it's kind of the average of our bootstrap replicates, and maybe we have very small error bars around that. So the values cluster very tightly around that mean value of K1, whereas maybe K2, we've got very big error bars. We can't learn that one reliably. Then we would know that the model is not so sensitive with respect to K2, but is sensitive with respect to K1. Or conversely, we can say we have high confidence in K1, low confidence in K2. You have to be a little careful there because it doesn't always make sense to subsample your data. So if you've got one set of curves you can work with, you don't really have independence between different points in time. There may not be an obvious way to do this kind of subsampling. That's often something we would want to do here. You also, just as in the case of this kind of sampling over perturbations of the parameters, you need to be a bit careful in that there may be complicated dependencies among these parameters. So it might be that you learn a model that tells you that K1 and K2 both have very high uncertainty, but it turns out that if you plot the values you get in the K1, K2 space over repeated bootstrap trials, maybe it ends up that all of your values fall in a region that looks something like this. So that might tell you that even though there's high uncertainty in the parameters, they have a low intrinsic dimension in the sense that there's a linear dependence between them, and maybe as long as that's preserved, you actually end up with a very good model for your data. So these are not necessarily easy problems to solve. You can get into pretty difficult kinds of visualization and statistical problems to figure out when there is substructure to your parameters, or to really characterize dependencies and uncertainties between different parameters. But this is often a question you really want to get into if you're trying to analyze a model in depth. All right, any questions about any of that? We do have one other alternative we can often use for this kind of sensitivity analysis, and we actually discussed this a bit in our example of learning gene regulatory networks. So if we're learning a gene regulatory network and we want to know which features of a model we should have high confidence in and which ones we shouldn't, how can we do that? What's a technique we had mentioned then? Well, often what you would want to do is pose your model inference as a sampling problem. So define a likelihood function for your training data with respect to the class of possible models, and then try to sample over the posterior distribution of models with respect to the data. So if you're learning a model structure, like a graph model, you can do a kind of sensitivity analysis to figure out that there are edges of the model that show up repeatedly or with very high probability in that posterior, and other edges that are maybe very uncertain, that show up sometimes and not others. And you can do analogous things with the quantitative parameters. So we could set up, for example, a Gibbs sampler over the strengths of the edges in a regulatory network model, and then based on that kind of Gibbs sampler, learn that some of these strengths are very tightly pinned down by the data we have available to us, and some are very uncertain, just like in this case. So often, these kinds of likelihood models can be generalized quite a bit, and in some fields, this is something you would do, you would be expected to do in analyzing a new model. So people who work in phylogenetics, for example, will often go to great depth to define these very detailed likelihood models and then really explore in depth the sampling over all the different parameters, the lengths of edges and mutation rates and all of that, to really characterize the model and see which things you can learn reliably. All right, so any questions about any of that? Right, so all of what I'm trying to do here is give you kind of a quick wrap-up of some of the important issues that go into model validation. And as with many of the topics in this class, I don't have time to go into any of them in depth. There's a lot more you can learn about all of these kinds of issues. A lot of what I'm talking about are things that have come up in a statistics class. So if you take advanced statistics, you'd often see in great depth these questions of how you evaluate models and learn from them and sample them. If any of you are thinking of going on to a field in model building and scientific research, it's often something I'd recommend. Get a really in-depth training in these kinds of statistical methods. Today, you would often learn that in machine learning contexts as well, so a lot of this you would now call machine learning rather than statistics. But basically, I'm just kind of trying to give you an overview of some of the general techniques, and hopefully these are things you can carry forward to future work you do. But what I wanted to do to kind of wrap things up is to go back to some of the questions we had dealt with all the way back at the beginning of the class in the first lecture, and really try to get into some of the more philosophical issues of what we should be thinking about in terms of building mathematical models or computational models of biological systems. And a lot of this really comes down to the question of the scientific method. So what does it really mean to do science? Because I think a lot of the things we would ask when talking about the philosophy of doing science in general are actually questions we should be asking when we think about how you do modeling or how you evaluate whether you've got a good model. So there is, in fact, a whole field known as the philosophy of science, some of you may be familiar with, and usually scientists and philosophers of science don't talk to one another very much. It's not considered by most scientists, I think, something that is practical. It's more of a curiosity. But I think if you're building modeling, understanding something about the philosophy of science is actually very useful to how we think about modeling. So I want to go through a bit of that kind of issue in the remaining few minutes of the class. And we can start by thinking about the scientific method as you might have seen it in previous classes. So roughly speaking, the scientific method is divided classically into 4 steps. You observe some natural system, you develop a hypothesis, so you get some model for how you think that system behaves. you test the hypothesis, and then you develop a theory. So you theorize, and typically your theory would be either your hypothesis is supported or it's not supported. And probably you've seen something like this presented as the scientific method. So how many of you are familiar with that concept? You've heard the term scientific method before? Okay, so some of you. So that is something you would often think of as the basis of doing scientific research. But philosophers of science would typically say that that's actually very oversimplified, that really doing science is a much more complicated question than that. And I can illustrate that by taking an example. In this case, it's actually an example from studies of physics. I've never quite found a good biology example, so I'm still trying to find one, but physics works fine for this. And in particular, an example of understanding the physics of gravity. So at one point, we understood gravity through a set of different laws that described how gravity acted in different sorts of situations. So Galileo had certain laws. So for example, Galileo had laws that told us how gravity behaves on Earth and how gravity is acting to put forces on anything on Earth. And at the same time, there were some laws from Kepler that talked about how gravity acted on celestial objects. So how a path of a planet traveling around the sun or whatever would behave as a function of gravity. And for a time, anyone who was interested in gravity would have to see which domain they were looking at. So are you looking at Earth, or are you looking at the skies, and figure out which law applied. Later on, Newton came along, and Newton's big contribution to gravity was to realize that Galileo's laws and Kepler's laws were both special cases of the same law. So he came up with his law of universal gravitation, which showed that the laws Galileo and Kepler had described both actually followed from a common universal law. Eventually, Einstein came along and developed general relativity, which said that Newton's law wasn't exactly right. It was right within the domains we could kind of easily observe, but there were special cases like near very large gravitational bodies or very high speeds where Newton's law wasn't actually quite correct. And most physicists, I think, would say that Einstein's law isn't the final thing. We're waiting to discover a more general law, and typically people would say this is going to be some kind of quantum gravity. So that's going to be the next thing we find, some way of reconciling the laws of gravity with our understanding of quantum mechanics. And this progression from the Galileo and Kepler laws to the unified Newton laws to Einstein and eventually probably to something else like quantum gravity illustrates some of the problems with the scientific method as a way of thinking about science, and also with how we should think about whether a model is good. So we can ask, for example, if Newton's laws, let's say, make the same predictions as Galileo's and Kepler's laws, did Newton actually do anything? It's maybe caricaturing a bit because there would be some situations where Galileo's and Kepler's laws, neither of them would exactly apply. But let's just say, for the sake of argument, that for any particular domain where we cared about gravity, we can either apply Galileo's laws or Kepler and get the same result as Newton's. Then did Newton actually do anything useful if there was no new prediction his laws could make? When Einstein came along with his laws, did he show that Newton had actually not accomplished anything? So if Einstein showed that Newton's law wasn't correct, what did Newton do that was worth, that had any value to it? And when the quantum gravity or whatever comes along, can we say the same thing about Einstein's laws? And even if that does come along, how will we know that we're done? How are we going to know that when we get to this point, we've actually got the final correct law and nothing else is going to show that that law is wrong? So these are the kinds of questions that a philosopher of science might ask. And there have been many people working for many centuries trying to answer these kinds of questions. So the question of, for example, Galileo and Kepler versus Newton, did Newton's law add anything, is often answered through a philosophical principle called Occam's razor. And Occam's razor is kind of a generic version of what we've been referring to as an anti-complexity prior. So Occam's razor basically says that if you have different models that can explain your data, then the simpler model is the better model. Kind of gives a way of thinking about why what Newton did was important in showing that there was one simple rule that captured these two more complicated rules. But even then, it's not so obvious why that would be a good thing to do. Why is Occam's razor the right thing to do? The question of whether Newton did anything or whether Einstein just showed that Newton's law had been completely wrong is another one that philosophers have kind of struggled with. So there's a general theory, comes from a philosopher scientist named Popper. So Popper basically put forth this idea that you can prove a model wrong, but you can't prove a model right. So you can come along and you can say that for a while Newton's model has not been proven wrong, and that's the best thing we have out there. But then Popper would say that when Einstein showed that there were conditions where Newton's law didn't work, he falsified Newton's law and showed that this was not in fact the right model, and then we can move on to a new model. Most scientists, I think, would say that even that is not quite right. So, or most philosophers of science, I guess I should say. One reason for this is that Newton's law was undeniably useful. It was actually useful for predicting a lot of things, for predicting things that maybe couldn't be predicted with the earlier laws. So it's not really quite correct to say that it was just shown wrong. It was right to a degree, and it may matter to what degree it was right. We also have the problem that we can't necessarily even be sure that a law was proven wrong. And we can use Galileo's law to illustrate that issue by taking a thought experiment that's often associated with Galileo. So one of the things Galileo's laws implied is that everything should accelerate at the same rate in Earth's gravity. There's a constant rate of acceleration. And there's a story with Galileo that he showed this by standing on top of a tower and dropping two cannonballs of different sizes off of the tower and showing that they hit the ground at the same time. Because most people before Galileo came along thought that the bigger cannonball would go faster, and he showed no, that's not actually the case. So that story, most historians think, probably didn't really happen. It wouldn't have exactly worked even if it had happened, because the air resistance would be acting differently on these. But let's just pretend that Galileo did this in a vacuum and he showed that they hit at the same time. We still couldn't be quite sure that he had shown that these were hitting at the same time versus different times. So at the time they lived, you didn't have really accurate atomic clocks, so you probably would have had someone watching some less accurate mechanical clock at the time, and maybe they would have reported that cannonball 1 hit at 10 seconds and cannonball 2 at 11 seconds, and then would we know if their precision for measurement is not better than a second, would we know that this actually hit before this? Or if it had been 10.001 versus 10.000, are these different numbers? Really depends, and we can't necessarily be sure. Even if we assume that Galileo had really accurate timepieces, we're assuming that Galileo was using those reliably. Maybe he was a brilliant guy, but was actually really sloppy in his measurements, and we can't actually trust his numbers. Or maybe his numbers didn't work out and he just lied about it because he didn't get the results he wanted. So these are issues philosophers of science worry about, and some of them kind of take this to the extreme and say that every scientist is a real person, there's uncertainty, we don't know who we can entirely trust, and they end up with a model called social constructivism. And social constructivism basically says that science isn't real. It's just kind of an agreement among people who call themselves scientists to decide that some things make sense and some don't make sense. You can't really believe any of it. Most philosophers of science are more measured in their thinking about this, and they don't really believe that nothing is real about science, but they do believe you have to account for this, that there are social constructs, there are social relationships, there are biases everyone has in their science, and that science is kind of approximating a ground truth and getting closer and closer over time, but you always have to interpret it within the window of how people think about these different problems. That is most often associated with a couple of philosophers named Ludwig Fleck and Thomas Kuhn. So Kuhn is best known for coining the term paradigm shift. People think about how to do a certain kind of science, and then every so often people kind of break out of that paradigm, show that another way of thinking about it leads to more accurate answers, and then they kind of start working in the new paradigm for a while. So that is more or less philosophy of science as of a few decades ago, and people keep thinking about these, and there's more and more information accumulating about them. But what I think all of this is getting at is that these are issues as modelers we need to worry about as well. When we're developing a model, we need to worry about not just is this model good, but in what domains is this model good? By what measures is the model good? Compared to what alternatives is it good? And we need to think about these maybe with more precision than a philosopher of science might typically think about them, because we really care about doing science. We're both scientists and philosophers of science. And I tried to summarize some of these thoughts in what I call a modeler's method, which is kind of a version of the scientific method to capture how we can think about these sorts of issues. So for a modeler, we need to be much more precise about these questions of what we mean when we're talking about the steps in the scientific method. And so we would need to say that, for example, we want to observe a particular process X in a particular domain of possible data sets S. We need to build a model, lambda of X in S, and typically we'll be learning lambda from some universe of models we need to be explicit about, and we need to build it with respect to some procedure for developing it. We need to evaluate lambda over samples from S, and often we need to be explicit about how we're sampling S by some objective function that makes sense for our problem. Let's call that phi, and then we need to identify domains S prime subset of S, where lambda is optimal by phi, and often they're optimal with respect to some other sets of models available to us. So what all of this is doing is really what we've been doing throughout this class, but it's just a way of thinking about all of the kinds of things we need to be careful about when we talk about whether a model is validated or whether it's a good model. And I think it's important to note that scientists in general are doing all of this. They're just not necessarily being as explicit about it as we need to be when we're building mathematical or computational models. So this is something I think when you work in modeling you need to be aware of, but actually when you work in any kind of scientific research, you're doing this, and I think you can be a more effective scientist if you're explicit about all of these kinds of assumptions you're making, and explicit about what you mean and what you're trying to do at each step of the analysis. So I know we're out of time here, so I think I'll just stop there, and then that will wrap things up for the term. Thanks. All right, so if anyone